2.6, section 2.6, we're going to talk about the chain rule. Now, what chain rule will do for us is it will help us find the derivative of more complicated expressions. And all of these functions that we use chain rule on end up being a function composition of two or more functions. Now, before I actually go through this theorem 1, which is the chain rule, let me just make up kind of an example that's easy to follow. Let's say in your automobiles, okay, suppose you have a car. Let me just put that up here, an example. Suppose you have a car, okay, your car gets, hypothetically, you get 30 miles per gallon in your car, okay? And let's say gasoline cost, the cost of gasoline is about $4 a gallon. I know right now it's lower, but just to make the numbers easy. So your car gets 30 miles a gallon. Notice that miles per gallon is a rate, and so is the $4 per gallon. Both of these are rates of change. We can think of them as rate of change. Now here's a question I want to ask. How many miles can you drive for each dollar? Okay, so I'm going to put the question, how many miles per dollar? So for example, can I drive 5 miles for $1? Can I drive 10 miles, 3 miles? What is it? So the way we work this is the following. Well, let's see. The car gets 30 miles per gallon, so that's my first rate. And if I multiply that by, for each gallon, I spend $4. Times 1/4, well, the gallons cross out, and I end up with 30 times 1 divided by 4. That's going to be 7.5 miles per dollars. We never talk about that, huh? We never thought about it either. We usually think about in terms of miles per gallon, but how about this? For each dollar, how many miles can you drive? So there you go, 7.5 miles per dollar. So this is an example of a function composition. So notice how to get this final rate, we had to multiply the two prior rates in order to get there, right? So let this be the inspiration for chain rule. Okay, and this is a theorem that we will not prove. We'll just look at the theorem the way it is. So in this theorem, chain rule, the theorem reads, if f is differentiable, okay, at x, and so is g, both f and g are differentiable functions at some point. So f is differentiable at x, g is differentiable at f of x. And we're going to call the composite function, this function composition, h of x, to be g of f of x. Then the derivative is given by g prime of f of x times f prime x. That's how you multiply the two rates together. Now, oftentimes with function compositions, we think about these functions as outside, inside. So the first function you begin with, that's on the outside. The second function is on the inside. So that's the idea of outside and inside functions. So the way the chain rule works, this will help you remember this, is that you multiply derivative of the outside function, that's all of this, times derivative of the inside function, that's what that is. Okay, and when you do that, that's the correct way of finding the derivative of these more complicated functions. Now, it does require that we recognize the composition, of course, right? Once we recognize the composition the right way, then it's easy to hit it with the chain rule and then get the right ideas here. Okay, so now here I have these alternative forms of chain rule for you, and we actually use all of them. So the first one, ddx of g of f of x, again, is g of f, the circle notation, g of f prime of x. That's more definitional form, not the practical actually working with it. That's just an alternative form using function composition notation. Now, if we let u, variable u, independent variable u, equal f of x, and if we let y be g of u, so that goes right in here. So we in effect have created a composition, right? And there you have it. So we have the composition of g of f of x. Okay, then if that is the case, then we can actually write dy dx as dy du times du dx. This form of it, by the way, this form is going to be really handy in third semester calculus. Okay, and it extends to higher order derivatives and with more number of independent variables with multivariables. Okay, and then I have this other form of it, which is ddx of g of u is g prime u du dx. That also is very common to use. So remember, what this form says is that you take the derivative of the outside, and then du dx is the derivative of the inside. The derivative of u is du dx. Okay, and once we have this chain rule defined, we can now generalize both of these theorems that we've seen before, right? We can generalize the power rule. So if we let y be u to the n, now this time u is a function of x. So remember, before we had x to the n. Now it doesn't have to be x. It could be cosine x cubed minus 5x squared. See, that to the fourth power, something like that. You see that? So we have the power rule. So the extended power rule, the generalized power rule, now accounts for u being a function of x. So you still use the power rule, but you just have to do chain rule, means the derivative of the inside. And if you look at both of these theorems, what I have, every one of these in the end has du dx, du dx. You see all of that? Every one of these have them. So all of that means is that you do things like you did before, but don't forget to find the derivative of the inside function also. So that's what that amounts to. Okay, and let me remove these. Okay, and that's all there is in this section. The key is to recognize the composition. Keep that in mind. So with that, let's take a look at these exercises now. In exercise, let's say number 6. In number 6, I would like to be able to find the derivative. Notice the instructions, by the way. In this one, question number 6, right in here, the author is asking you identify the inside function u and the outside function g of u, then find the derivative dy dx using chain rule. So let's try this one, and let me create some space. Alright, so in number 6 again, the equation is y is equal to secant of root x. So the outside function here is going to be secant x, right? That's the main function. And then the inside, this is outside, and the inside function is going to be square root of x, is the inside function. So in other words, we can see this. If I let, for example, if I let f of x, the inside function, be root x, and if I let g of x be secant of x, now you can see that if I do g of f of x, that would be g of root x, and that's g. Well, let's actually plug in for g now. G is secant, so that's going to be secant of root x. Okay, and there you have that one. Good. Now that's just recognizing outside and inside function. Now let's take the derivative. So by chain rule, first we do the derivative of the outside. So that's the derivative of just secant. Okay, derivative of secant x is going to be secant tangent. But remember, the argument of secant is f of x. So secant of f of x times tangent of f of x. And we've done derivative of the outside. And then we're going to go times derivative of the inside, which is the square root of x. And square root of x, we know root x is x to a half, right? So the derivative of that is going to be 1/2 x to negative a half. And we can now finish it off. So I'm just going to write the without negative exponents. So that's secant root x tangent of root x divided by 2 square root of x. And we're good with this one. Okay. And there is number 6. Okay. Let's take a look at another one, number 12. Okay. In exercise number 12, I'm going to write it and scroll. This is f of x is equal to x squared plus 3 divided by x to the negative second exponent. Okay. So let's do the same thing. Let's identify the outside and the inside function. Now for the outside function, again, the way I envision this function is this. I have something in here to the negative 2. So that's going to be my outside function. So I tend not to look at what's inside parentheses. Okay, so this is going to be my g of x. So my main function is that function raised to a negative 2. So if I take the derivative of something, there you go, to a negative 2, what's the derivative of that's going to be? It's going to be negative 2, right, times whatever that is. Negative 2 minus 1 is negative 3, isn't it? So that's what I'm going to do. F prime of x is derivative of the outside is negative 2 times, there you go. You can even leave it blank for now. But that's the derivative of the outside function. Now, I cannot leave it, of course, blank, so I'm going to fill it in with the actual function. Now, here's where chain rule kicks in. The inside function, derivative of the inside function. So what is the inside function now? Of course, it's the fraction x squared plus 3 over x. For that, I have to use the quotient rule, don't I? So I'm going to square the denominator and repeat denominator times derivative of the numerator minus numerator times derivative of the denominator. And again, that denominator, not the one that we just squared. And there we have this one. So for question number 12 now, this is going to be, to do this correctly, the expression with negative exponent, I'm going to flip that fraction and change negative 3 to a positive 3, okay? So it's going to be negative 2 times x over x squared plus 3 cubed. And then let's work in the fraction in front. X times 2x, that's 2x squared, negative x squared, minus 3, right? And we have like terms in that one. So let's bring it together. In front, I have negative 2x cubed times 2x squared minus x squared is just x squared minus 3. And it's being multiplied, so that's why I'm times them in the numerator. In the denominator, we have x squared, and then we have x squared plus 3, denominator of our first fraction. That's going to be cubed. That's this part. Okay. And let's see, we can cross out. Certainly we can cross out x squared and x cubed. That leaves me with just an x on the outside of parentheses. So this is going to be, and I'm going to distribute the negative inside the binomial. Okay, I'm going to distribute to the binomial, which is going to cause the change on x squared. The sign on x squared becomes negative, and negative 3 becomes positive. So it becomes x, the remaining x on the outside, and the 2, of course. Inside, I have 3 minus x squared. You see, I distributed the sign inside. And that's divided by x squared plus 3. That's x squared plus 3. And let me, again, my pen is acting here. Plus 3 quantity cubed. And there we have that one. So that's going to be the final answer for this exercise. Let's take a look at another one. This was number 12. Let's do number 20. In number 20, this one. Number 20, I have x squared plus root x to the 6th power. X squared plus root x to the 6th. to the 6th power, and that's number 20, the one we're doing. Here's our f of x. Okay, again on the outside function, let's go f prime of x equals. The outside function, again, I see this as, I view this as, doesn't matter what's in here. So I have a power, something to a power, I use the power rule. It's going to be 6 times the content of parentheses to the 5th power, right? And then derivative of the inside. Inside I have x squared. Well, let me put this before I forget it. Now times, here's where the chain rule comes in, times 2x plus derivative of square root of x is 1 over 2 root x. We've done that many times. You can verify it. We did it earlier, in fact, in the lectures too. And let's see what's going to happen to this one. As far as simplifying, I'm just going to put the outside function, x squared plus root x to the 5th times, this is going to be multiply the top bottom of 2x by 2 root x. So I can combine the fractions. 1 over 2 root x. There you go. There's nothing I'm going to do to the binomial in front. And because you have a radical and a polynomial function, they don't combine well. So times, this is going to be 2 root x. And in the numerator, I have 2 times 2. That's 4x root x plus 1. And that's good enough for me as far as we can take this one. Okay. Now let's take a look at another exercise. We just did number 20, right? Let's look at 24 is what I have circled. T plus 1 cubed over t squared plus 2t squared. T plus 1 cubed. Okay. Number 24. That was y, I believe. So it was t plus 1 cubed over t squared plus 2t. Quantity squared, not cubed. Quantity squared. Okay. Now, for this one, again, there are different ways we can do this. One way, if you want to avoid quotient rule, we can rewrite it like this. I can rewrite this as t plus 1 cubed. This is just algebraic step. T squared plus 2t to negative 2. And this way, I'm looking at it in the form of a product. Some people prefer to work product rule than they do quotient rule, because quotient rule ends up being messy. But in the end, we're all going to simplify it anyhow. So let's do derivative of the first one. The derivative of the first one, the power rule. 3 times t plus 1 squared, right? That's the derivative of the outside. Now, inside is t plus 1. I'm just going to write it so you know that I didn't forget it. The derivative of t plus 1 is 1. That's where that comes from. Okay? That's the derivative of the first function times the second, t squared plus 2t negative 2. So I did derivative of first by second plus first times derivative of the second. The second is this one now. This itself is a function composition. Outside function is like something to a negative 2 power. So that derivative is going to be times negative 2 times inside, whatever the inside is. And we raise that to negative 3 power now, right? That's the power rule. And then chain rule handles the derivative of the inside. Okay, inside is t squared plus 2t. That's times 2t plus 2. So fairly complicated expression. All right. Now let's clean this up a little bit as much as we can. Okay. So how are we going to simplify this? We can actually factor, let's see, this is a GCF. Remember, we are adding two big expressions, right? Two long expressions together. So I can factor t plus 1 squared. That's the GCF, right? I'm going to factor that. And t squared plus 2t. This is also common, right, to both. I can factor t squared plus 2t to negative 2 from that. So when I do that, my factored form therefore becomes t plus 1 squared, that's the GCF, and then t squared plus 2t to negative 2 factored out. What's left? Well, from all of this, all that remains is a 3, isn't it? Right? 3. And then from the other side, from this side, what do I have? I have plus, there's a t plus 1 here, right? Times 2t plus 2, this part, and then times negative 2 times t squared plus 2t to negative 1. Right, that's all that remains from the other side. True, just to make sure, let me pause and make sure this looks right. Good, I'll be back. All right, let's simplify this thing now. I'm going to keep the front for now and work inside the bracket. Okay, inside the bracket, let's do this. I'm going to write this as 3 negative. I'm gonna this negative 2. I'm gonna write it as negative 2 times and FOIL this. Do we get what? 2t squared plus 2t plus 2t plus 2 when you FOIL it, right? And then we're gonna divide it actually by t squared plus 2t. That's the denominator. So I just rewrote the denominator, and let me do this. So that's the next step, is to just look at the bracket. Now again, I can get the LCD. The LCD is t squared plus 2t, so that's 3 times 3 times t squared plus 2t. Hold on. 3. Okay, so it's going to be 3 times t squared plus 2t, right? That's the LCD, over t squared plus 2t, and negative, distribute 2 and combine like terms, so I get negative 4t squared. Middle terms 2 and 2, 4t by 2 makes actually negative 8t, because we multiply negative 2. Negative 2 by 2 is negative 4. And we can combine like terms, distribute and combine like terms. So in the next step, I have t plus 1 squared, t squared plus 2t to negative 2 plus, I'm not sure, this pen isn't cooperating again. That's t plus 1. Okay, t squared plus 2t to negative 2. Now inside the bracket, it's going to become t squared plus 2t, and distribute 3t squared minus 4t squared is negative t squared. Distribute 3 times 2, 6t minus 8t is negative 2t, and then there's negative 4. So it looks better now. And let me move this below. Okay, next step, and we're almost done with this. Here's our next step. I'm going to factor negative from this polynomial on top, okay, in the numerator. Factor the negative. So this becomes negative of t plus 1 squared times t squared plus 2t plus 4 divided by, move this binomial to the denominator So it becomes a positive exponent of 2 and then times this. So the denominator is going to look like this. It's going to be t squared plus 2t squared multiplied by another factor of t squared plus 2t. So now combined, there are 3 binomial factors in the denominator, so that's just going to be t squared plus 2t cubed, and that should do it. Okay, and there's the answer. Lo and behold, the answer falls right out. This one took longer again because, now personally I would have done quotient rule. I'm doing this because, again, some people like doing it this way, so I just want to show you the process. You can do it this way. You might want to try this using quotient rule, and I think you may find it easier actually in doing it with the quotient rule. Okay, so let me move this below and let's take a look at another example. So we did, which one? We did number 24. Number 30, cosine of x cubed. Okay, we're doing cosine of x, hold on, cosine of x cubed. Okay, we want to find the derivative of that. So again, the outside function is cosine, derivative of cosine is sine. And then the inside is x cubed, derivative of that is 3x squared, and there's the answer. And that's it. We're done with this one. How do I write the answer in the end? I put the algebraics first, usually we do, and then put all the transcendental next. And there you have it. So that was fairly easy coming out of the previous one, right? So it's negative 3x squared sine x cubed. To make up for number 24, that was overly long. And then let's take a look at number 34. In 34, tan squared plus, oh, this is tricky. Let me write it. Tan squared x, cotan x squared. Those are 2 different kind of x squares, aren't they? So in number 34, again, we have, this is going to be, oops, let me move this back a little. Okay, so number 34, again, the function f of x is tangent, we said, of squared x plus cotangent of x squared. Now the first one, you can rewrite tan squared x like that as tan x quantity squared, right? So we have the power. And then the second one, you actually have cotangent of a power. So f prime in this case, f prime of x is going to be derivative of the outside, that's 2 times tan x. And then chain rule, derivative of tan, which is inside, is going to be secant squared x. Plus, derivative of cotan is going to be negative cosecant squared x, right? X squared, that's the derivative of cotangent. Doesn't matter what's inside, it's going to be negative cosecant squared, times chain rule, derivative of x squared is 2x. Okay, so let me write down the final answer for this one. F prime of x is going to be number 34, 2 tan x secant squared x, right? That's the first part. And the latter part is 2x negative, that is negative 2x cosecant squared x squared. Negative 2x cosecant squared of x squared, like that. Or if we don't really need parentheses, as long as you know what's going on with that. And there's number 34. Number 34. And let's look at another one. This next one, number 34, we did number 40. Number 40, we're doing 2 plus 3 tan 2x. Okay. And then we do 46. Number 40. Here we have f of x 2 plus 3 tan 2x. And then the square root of that. Okay, so f prime of x is going to be, again, the outside function is whatever is the radicand to 1/2 power. So it's going to be 1/2 of the inside, 2 plus 3 tan 2x to negative 1/2 times derivative of the inside. Now inside derivative of 2 is 0, and derivative of tangent, this itself is a chain rule. Derivative of a constant multiple of tangent, that's going to be 3 times secant squared 2x times 2, that's the chain rule. And again, be careful, don't multiply these to 4x. That's incorrect, because 2x here is the argument of secant. That's just you cannot multiply it by the number on the outside. And there you go. So let's bring this home. Again, clean this one up. So f prime of x, the negative exponents, remember, those go in the denominator, right? So this is going to be 1 over 2 times 3, that's 6 secant squared 2x divided by, and I'm going to put the parentheses in the denominator, and in number 40 we're going to use a square root. Oh, actually, I just realized the 2 and the half cross out, so that's just 3. And that's the square root of 2 plus 3 tangent of 2x. Okay, and that is your number 40 for you. One last one from that segment. We're going to do number 46. T plus tan 3t. Number 46. G of t was the square root of t plus tan 3t. Right, that's number 46. Now for this one, let's take the derivative again. So g prime t, again, the outside function is like to a half, right? Something to a half. Square root means radicand to a 1/2. So g prime t is going to be 1/2 t plus tangent 3t to negative 1/2 times derivative of inside, derivative of t is 1, plus derivative of tan 3t, derivative of tan is secant squared 3t, but then that 3t inside, you see that itself is a composition. 3t is composed with tangent. So we're going to do times 3 close paren. And that is the correct derivative. Okay, again, let's bring this one home. G prime t is equal to, the half is going to stay in this one, right? So I'm going to have half. In parentheses, we have 1 plus 3 secant squared. 1 plus 3 secant squared 3t divided by 2 times square root of t plus tan 3t. Notice all of a sudden our derivatives are much more complicated, aren't they? And because the functions we're given are more complex, so they really, without chain rule, previous sections methods would not do this correctly. We wouldn't be able to get the correct answers. And we are good in that segment. I think we did all the ones that I had circled, quite a few. See how many I did. 2, 4, 6, 8. Not bad. Now let's take a look at this segment. Now in this segment, let's do maybe a few of these. I don't know which ones. How about let's take a look at number 54 and we look at number, trying to stay with the even numbers, 54 and 56, and maybe one last one would be 60. Okay, and that will conclude it for us. So in number 54, first that one, number 54, we have g of t is tangent of cosine of 2t. So it's tangent of something, right? The derivative, g prime t, derivative of tan is secant squared of whatever, times the inside function is cosine, derivative of cosine is negative sine 2t, but then notice the cosine itself is made up of a composition, so we're going to multiply by derivative of 2t, which is 2. Remember, we go as many layers as there are in order to reach the answer, as many layers as possible. So this is going to be negative 2 sine 2t cosine 2t times, oh, I'm sorry, I made a big mistake myself. Let me just show you where I went wrong. There you go. That's the argument. Again, cosine 2t is the argument of secant, so don't make my mistake. Don't multiply them. And that's secant squared of cosine 2t. And there you go. We're done with number 54. Okay, negative 2 sine 2t secant squared cosine 2t. Now let's do, that was 54, let's do 56. In exercise number 56, we have y is equal to the square root of sine of cosine 2x. So the outside function is square root, inside function is sine of something, the cosine itself a composition, right, of something. Finally, the last layer of the onion is 2x. So we're going to take 1, 2, 3, 4 derivatives here, right, for the 4 layers, working from outside to inside. So we get y prime is, let me make room because I'm going to need the whole line for this. Okay, derivative of the outside, so that's going to be 1/2 sine of cosine 2x to negative 1/2. That's derivative of the outside. Then we move one layer inside to the radicand. Derivative of sine is going to be cosine of whatever is inside times. Every one of these is chain rule. And then derivative of sine was cosine. Derivative of cosine 2x is going to be negative sine 2x, and derivative of 2x is 2. You see how many times you had to do chain rule in this one? Again, because you can think of this as like this would be in the form of here. I'm going to go f of x is root x. G of x would be sine x. H of x is cosine 2x. And I of x is just 2x. Or right? So when we do this composition, we're doing, for example, f of g of x. What would that do for us? That would do square root of sine x, right? See, it looks kind of like the number 56. So this is really f of g in the form f of g of h of I of x. 1, 2, 3, 4 parentheses closing. Look at that composition with that one. True? H of x instead of cosine 2x. I'm sorry, that's cosine x. There, now it looks right. And there you have it. So anyway, let's continue on with this one. So how am I going to simplify the 2 and the half cross out? So in the numerator, I'm going to have negative sine 2x times cosine of cosine 2x, all of that divided by sine of cosine 2x to 1/2, which we write as a square root. That's just to make it look like the original problem. Okay, because they gave us a square root, we're going to give them back the square root. And for number 56, let me make sure yeah, I'm good with that one. So that's going to be the answer to number 56. But check out this composition, isn't that cool? Once my pen works, it looks cool. There you go. Now, we did number 56. Let's do the last one. We want to find the second derivative in this one. In number 60, we have x sine 1 over x. The second derivative, number 60. Y x times sine 1 over x. Now, looks pretty innocent, right? But it's probably going to get really messy. Y prime, product rule, derivative of first by second plus first times derivative of sine, cosine. But then inside is 1 over x. Now 1 over x is like x to negative 1, isn't it? Derivative of that, use the power rule, negative 1x to negative 2, so that's negative 1 over x squared. That's what I'm going to write. Times negative 1 over x squared. Again, I emphasize times like that because I don't want you to multiply these, right? Because there you go, that cosine 1 over x, the argument, we cannot penetrate that from the outside with another function. So this is going to be sine 1 over x. The x here and 1x in the denominator cross out. Plus becomes minus because there is a negative here. So it's going to be negative, and this is going to be 1 over x times cosine 1 over x. So that's our first derivative, right? The first derivative is not bad. That's manageable. Okay, now let's do our second derivative. So this is y prime, we want to do y double prime. Now y double prime, which is going to be, that's like the second derivative of y with respect to x, the x squared. Okay. So we have the derivative of sine 1 over x, that's going to be cosine 1 over x times derivative of 1 over x, we just showed is negative 1 over x squared. Minus, we're doing this part now. Derivative of 1 over x. That's that times second plus 1 over x times derivative of cosine is negative sine, right? Negative sine of 1 over x times the derivative of inside 1 over x, which is negative 1 over x squared. Okay. Now this becomes negative 1 over x squared cosine 1 over x. Now inside parentheses, let's see. Here we're going to distribute negative, so we get plus 1 over x squared cosine 1 over x. That's good because I just see opposites. Those are opposites. That's good. In fact, let's get rid of them. And then distribute the negative outside the bracket. Remember, there's negative on the last fraction that makes positive, right? And that's going to be positive. Oh, and then there is a negative here. So there are 3 negatives in this one, right? There's this negative, and this negative. So those 3 negatives multiply to negative. That's going to make this negative of x here, x squared here. So that's 1 over x cubed, and then sine 1 over x, right? And that's the final answer. Not too bad. Y double prime, which is d squared y dx squared in Leibniz notation, is negative 1 over x cubed sine 1 over x. And there you have it. So we are done with this section. We did, I feel good. We did a good number of exercises here. And with that, we are done with this section, chain rule, something that we will definitely look at in future sections and chapters, and you will definitely work with this in your other engineering classes as well. Okay, with that, we are done with section 2.6.